Welcome back. Today, this will be our 10th lesson for ETAP software tutorial. Okay, the topic that we will be discussing today is one of the module from ETAP, which is the optical capacitor placement. The majority of power systems operate at a lagging power factor due to inductive loads and delivery apparatus, that is lines and transformers. Power systems are inductive in nature and require additional reactive power flow from the power grid. But excessive reactive power demands result in reduced system capacity, increased losses, and decreased voltage, as well as higher operating costs. Shunt capacitor banks are able to compensate for VAR requirements. But bank size, location, the capacitor control method, and cost considerations are important issues that need to be optimized during the design phase. An ideal solution would be a capacitor placement tool able to weigh all these factors, and that considers load levels. This solution should also be able to place capacitors for voltage support and power factor connection, while minimizing the total cost of installation and operation. Okay, so this will be our model one-line diagram. Okay, so we have here our power grid, which is 150 power grid connected to bus 1. Here, we have here 3-winding transformer and a 2-winding transformer. From our 3-winding transformer, the primary, secondary, and tertiary rating is 20, 10, 10 MVA respectively. This 3-winding transformer is being stepped down from 115 kV to 13.8 kV. Okay, so we have here also our a 2-winding transformer rated 15 MVA, and it is being stepped down from 115 kV to 13.8 kV. Okay, so I have here also a 10 megawatt generator. It is used for voltage control, which is this 2-winding transformer and this generator are being connected to bus 4. Okay, so on bus 2, we have here a load which is rated, lamp load rather, which is rated 5 MVA. At the bottom, okay, we have here our composite network. Okay, let's click this composite network, what is inside. Okay, so we have here two transformers which are connected in parallel, rated 6 MVA, and is being stepped down from 13.8 kV to 4.16 kV. Okay, from bus 5, 4.16 kV bus, we have here one synchronous motor, okay, this one. Two numbers, 2,000 horsepower. Okay. And downstream, we have also here 4 numbers, 500 horsepower motor connected to bus 7, the same 4.16 kV bus. And we have here an static load rated 2 MVA. Okay. On the other side, we have here one 2,000 horsepower induction motor. Okay. And we have also here a 2-winding transformer, a 3 MVA. Okay. And a step down from 4.16 kV to low voltage, 480 volts. Okay, so from this bus 8, the 480 volt bus, we have here our composite motor. Okay, let's click this, what is inside. Okay, from this MCC from here, okay, we have different sizes of motors. We have here 4 numbers of 200 horsepower, 5 numbers of 100 horsepower, and 1 number 250 horsepower, and a static load which is rated 1 MVA. Okay, let's go back to the 150 kV bus. Okay, let's click this OLV1. Okay, we have here. Now, to verify, uh, let's run a load flow analysis to verify on our, to investigate whether we have any voltage deviation on our buses. Okay, so let's go and click this load flow. Okay, load flow. And from the right side, we have this run load flow, and let's click on this. Okay, right now for our bus 1 on the 115 kV bus, we have 100%. So there's no issue for the voltage deviation. Okay, on the bus 2, we have here 98.83% against the nominal voltage, which is still okay. On the bus 3, we have here 98.96%, okay, which is also acceptable. And on the bus 4, we have here 98.93, which is also acceptable with regards to voltage deviation on the bus. Okay, let's check on our composite network on the bottom of our this single line diagram. Okay. Okay, so we have here bus 5 and bus 6. If you the color of the bus is in pink, meaning these buses are in marginal value. Okay, from here you have here 96.31%, and on the bus 6, that was bus 5, and on the bus 6 here we have here 96.31%. Okay, so it is in marginal value. But here, if you are from here on the bus 7, it is red right now. Imagine the bus voltage here is around 93.1% against the nominal voltage, which is beyond on our requirement for the critical, which is up to 95%. We have here 93.1%. On the bus 8, same issue, because we have here, it's in red also. We have here, meaning this is in critical value. We have here 94.19%. Okay, so one of the solution to correct the voltage deviation on the buses is to change the top setting of our transformer, the T3 and the T4 transformer. Okay, so first, let's change and we rerun again the load flow analysis, and let's verify whether this voltage deviation are still exist. Okay, let's start on transformer T3. Okay, and let's change to adjust to increase the bus voltage. Okay, we'll just on the primary side, let's select let's say let's provide here a negative 2.5, okay, percent tapping, and let's click OK on this. And on the transformer T4, the same thing. Okay, and let's go to the top setting. Okay, also 2.5. Okay, we have here negative 2.5, and let's click OK. Okay, now let's check whether we have an improvement or an acceptable bus voltage or bus deviation on our buses from this 4.60 kV bus, the bus 5 and bus 6, and also for our bus 7 and bus 8. Okay, so let's run again the load flow analysis. This one. Let's click this run load flow. Okay. So right now on the bus 5, we have improved. And now before it was in pink color, now it is in black now, which is the bus voltage is around 98.91% for against the nominal voltage. The same thing for bus 6, we have also here 98.91%, which is already acceptable. Okay, but on the bus 7 and bus 8, still not acceptable because we still have a marginal value here which is rated 95.74% on the bus 7, and here on the bus 8 we have 96.85%. Okay, so instead of again changing the top changer, we have another solution to correct the voltage deviation of these two buses, this bus 7 right now and bus 8. Okay, so one of the solution for that one is to run this module from ETAP, which is the optimal capacitor placement. Okay, by adding a capacitor on the system, this will first improve the power factor, and second, it will correct also the bus voltage deviation. Okay, so let's but before that, okay, let's click this, okay, optimal capacitor placement. Okay, and let's go to the study case. Okay, so from the study case, okay, let's check or click this voltage constraint from here. Okay, so the buses that we're going to correct right now is bus 7 and bus 8, right? So let's select this bus 7. Okay, so here the maximum voltage, okay, let's limit into 105%, and the minimum voltage let's limit to 98%. Okay, so let's select bus 7, select, and the bus 8 also, select from here. And also from here, this global constraint, we need to adjust as well that maximum voltage here, the same, 105%, and the minimum voltage to be 98%. Okay, so next, we have, after this voltage constraint, let's click this power factor constraint as well. Okay, okay, so from the power factor, our setting here is minimum. Let's say that we need to have a minimum, in our study case, we're going to choose minimum power factor to be 95%. Okay, so from here, the maximum 5%, of course, 100, and the minimum, we're going to select 95%. Okay, so the bus that we will have, that we are having an issue is bus 7 and bus 8, right? Okay, so let's click this, select, and let's click also this one, select. After that, we have to go to this section from here, this one, capacitor. Okay, let's click this. Okay, so okay, we are now already here. Okay, so our bus 7 is rated 4.16 kV. Okay, and our bus 8 is 0.48 kV. So we have already here rated 0.48 kV. We need to check if we have here 4.16 kV. Just hold on. Okay, so we have here number 11, 4.16 kV already. So this is fine. Okay, so let's select again this one. Okay, the bus candidates to be bus 7, add, and bus 8. Let's add from here. Okay, and let's click OK on this. Okay, I think we are ready now to run the optimal capacitor placement. Okay, this option, ETAP will going to provide us the recommendation whether bus 7, bus 8 will have a capacitor, and also ETAP also will recommend us the rating and the number of the capacitor banks. Okay, so let's click on this, run optimal capacitor placement. Okay, Okay, so we have here on the bus 7, ETAP recommended to provide a capacitor bank 8 total banks, which is rated 1,537 kbar. Okay, here the 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 capacity for each capacitor is 200 kvar. Here 8 numbers, right? Okay. On the bus 8, ATAP also has recommended to provide 6 numbers of capacitor banks, okay, which is rated 100 kbar. Here 200, here 100. Okay. So right now, we're going to update our single line diagram. Okay. Let's extend from this side. Okay. And this one also let's extend from this side. Okay. And now we're going to add here the capacitor that was being recommended by ETAP software. Okay, so let's start on bus 7. Okay, let's update the single line diagram right now. Okay, so let's add a capacitor from here. Okay, let's connect here. So from here, the capacitor rating, the recommendation from ETAP is 200. This is keybar. Okay, let's change this one from inbar. Let's change this one to keybar. Okay, just hold on. Keybar. Okay, so we have here 200, and it's the recommendation is 8 numbers. Okay, so we have here already 200 keybar and 8 number of banks. Okay, okay, so maximum kV is 4.16. Okay. Okay, so let's close this. Let's click OK on this. On the 480 volt bus, we need to add also capacitor, okay, as per the recommendation by the software. Okay, from here. Okay, so from here, ETAP recommended, okay, let's change this one into keybar. Okay, ETAP recommended to be 100 kbar only and 6 numbers. Okay, so 6 numbers from here, and the maximum is 0.448 kV, 480 volts. Then let's click OK on this. Okay, now we're going to verify after providing 2 sets of capacitor banks on bus 7 and bus 8 whether our voltage deviation has been corrected. For that, we're going to run again a load flow analysis. So let's go from here, load flow. Okay, and this, let's click this run load flow again. Okay, run load flow. Okay, so this is our final result now after running the load flow. We have tremendously, or we can say that we are already corrected the bus deviation for bus 5, bus 6, 7, and 8. Right now for bus 5, we have here 100.6%, okay? And also for the bus 6, we have 100.6%. Imagine for bus 7, we have around 95% before, and now we have already 100.1%. And also for bus 8, it's around 99.96% against the nominal voltage. Meaning, after adding the capacitor bank on bus 7 and bus 8, the system, the capacitor bank has corrected not only the power factor, okay, the capacitor bank also corrected and improved the voltage deviation on, especially on the bus 7 and bus 8. Okay, thanks for watching.